Okay, so let's go ahead and start recording again. Parametric equations. So as I was mentioning, we want to start moving calculus into 3 dimensions. We're still going to work in 2, though, for the rest of the semester. If you have to move on to Calc 3, then you'll start working in 3 dimensions. And as I was saying before, well, we have this notion of a function, right? So function, we have relationships between 2 variables. An independent and a dependent. And of course, there's only one output for each input. And we've ran into a little bit of problems with this. So far in calculus, this has covered the basics of any time we want to relate 2 variables. Functions are essentially the first thing we're going to think of. But sometimes functions don't work. So for example, if we wanted to model a circle, well, what's our problem with a circle? Don't always work for, let's say, all models. Because sometimes we have things, equations, like x squared plus y squared equals, let's say, 16. So our circle of radius 4, centered at the origin. And our problem is that if I try to solve for y, we actually have this plus or minus. And we have to model a circle with 2 functions. And this is whether we solve for x or solve for y, right? Conversely, if I tried to write x as a function of y, we would get essentially the same thing. And in either case, there's kind of like not a natural choice of independent versus dependent variable. We do have other situations, right? So far, we like things like y is x squared. This is nice because it matches y, our dependent variable, as a function of x. And so you could be modeling some sort of rate of change. So for example, like position or speed. If you throw a ball up in the air, we've seen a lot of parabolas where we're modeling this real world situation where the height is now a function of maybe time. Or you can even model things if you're throwing things horizontally or accelerating a car. You can measure the distance as a function of speed. And there are models where you can get parabolas. Of course, sometimes we can flip that, and if we have x is equal to y squared, well, y isn't a function of x, but in this case, I can write x as a function of y. And this is nice as well. We just have to think maybe a little differently in terms of what we choose as our independent variable and what we choose as our dependent variable. In a real world context, well, it's kind of our choice, right? If I have 2 variables, you can always switch the axes and relabel them. This is my time variable. This is my space variable. This is my volume variable. This is my radius variable for measuring the rate of change of water flow or something like that in a tank. And so it's kind of arbitrary which way we choose the axes. As long as we can write one variable as a function of the other ones, we're kind of happy with that. We can do calculus on that. I know how to take derivatives. We could change the variables if we wanted to. We haven't gotten much into how to change variables in calculus, but we'll do a little bit of that in Calc 3. But of course, with these circles, well, now we can't even write one function as the other. There's no natural choice for which one is the independent, which one is the dependent. They are essentially related to each other, and we could kind of think of it as implicit functions, which we've also seen. Sometimes we can't solve y's in terms of x's. And so what we want to do is come up with a new way of modeling certain curves in space. In many ways, you can kind of think about this as a particle moving in space. So think of a particle. It could be a billiard ball. And the key thing now is that we're actually in a two-dimensional space. So I'm going to write, so this R means real numbers. When I write R2, this is our 2D plane, our XY plane, essentially. If I write R3, we won't use that in this class, but if you see R3, it's a 3D plane. Actually, I think in the activity for some of these parametric equations, they have you model in 3D space a little bit. Not too complicated. It's just taking an XY plane and then now adding a Z axis. So far when we've modeled things that are moving, we've said like a particle moves in the x-axis. So it'll move along the x-axis, and we might give a function with how it moves. So think of our spring, for example. If I stretch a spring and then let it go, it's going to oscillate on the x-axis. But now we have a particle moving in a 2D plane. So you could think of it as just starting somewhere, and then it's going to move around, and as it moves, well, of course, it traces out a curve. And it could even go over itself and then come back. Sometimes it comes back to where it starts. Sometimes we have other particles that might just start somewhere, and they could just go off and continue. Depending on the bounds and how we model it, really what we're going to consider it as like the time frame in which this particle moves. It could be, we could consider a time frame from 0 to infinity. We could consider a time frame from minus infinity to infinity, and that will kind of give us the bounds of the curve of when it starts and when it stops. And then we want to learn the algebra of, well, how do I draw these curves? So that's our idea. So what's happening is we can model the position of the particle as it moves in time. What's this mean? So this means, well, what's the position of the particle going to be given as? We write position, if it's on a two-dimensional plane, it's going to have x and y coordinates. But the xy coordinates are changing in time. So we sort of introduce this extra independent variable, which is time. And so we commonly write this as x of t, x as a function of t, y as a function of t. And you'll see brackets or some sort of squirrely bracket on the left. And then often we have a time constraint. So we will have our bounds for when this particle is moving. So now it's almost like we are making x and y, since there's no natural choice sometimes of which one's independent, which one's dependent. We make x and y both dependent variables and then have time be our independent variable and see how both of those are simultaneously changing in time. Let's do some examples. So the easiest example is to do something like lines. Let's say x of t is equal to t and y of t is equal to, let me pull out my examples. Is equal to, let's say, t squared. And we'll give bounds for t between minus infinity to infinity. So how do we plot something like this? One way we could always do, as we've done with any plots, is make a table. So let's plot our t, our x position, and our y position. So have minus 2, minus 1, 0, 1, and 2. So x of t is just equal to t. So those are pretty easy. And then what is y? Y says take t and square it. So we will get 4, 1, 0, 1, and 4. And now my xy's, these are points. So if we were to draw it, let's try to get our axes as close to precise as I can. So at time -2, I am at the position -2, 4. I have the point -1, 1, 0, 0, 1, 1, and 2, 4. And so what's going to happen? So if time was starting at -2, I would go from here down to this point, down to 0, curve, and come back. And of course, since time continues positively, it would go off that way. And since we started only at -2, but we want to go off to negative infinity, if we reverse time, it'll go back the other way. And we see a parabola, which hopefully some of you guys can kind of expect, because if I wanted to get rid of this independent variable, my time, well, since x is equal to t, you could substitute your x in for that t, and you should see y is equal to x squared. And we see a graph of a parabola. This is actually very common for parametric equations. So given any function, we can model a function by a parametric equation just by setting x equal to this dependent or this independent variable. Right? We're trying to introduce this dummy independent variable of time, but it is often easiest enough if I wanted to take a standard equation and then write it as a parametric equation to just let x be that dummy variable equal to t. So for example, we could do some easy things like lines. X of t is t, and y of t is minus 1/2 t, say plus 4. So we could draw a table again, but another way we could recognize it is just to see, well, is there a substitution I can do? Can I somehow recover a function from a parametric equations? And sometimes we can. So it is something to look for. So for example, since my x is just my dummy variable, t, I can replace this t with x, and we get y is equal to negative 1/2 x plus 4. And if we were to try to graph this, of course, we're just graphing a line now. And so we get something like this. So, and of course, we can recover these points. What's going on there? If we were to make our table, we can, well, what happens when t is 0? My x is 0, and my y is 4. Then I go 1 on the x, which means my time is 1. So I go down 1 over 2. Oh, sorry. My t was 2. X would be 2. And then y would be 3. And this point, since I'm going down 1, right 2 again, my time there for that one was 4. And we recover those points. So sometimes we can recover information from parametric equations, or vice versa. I could be given a function, and if I want to come up with parametric equations for it, we could easily enough is that on screen? Nope. If we're given a function y is equal to f of x, we can parameterize easily by just setting x equal to t, and then y equal to that same function just changed to the variable. So for example, let's do a harder parabola one, or one with a little more, something a little more involved. So let's say y is equal to negative, let's say x minus 4 times x. So we can graph this. And well, so how do we standardly graph this? My zeros are going to be at 0 and 4. Where's the max going to be at? So the max should be at x equals 2. So if I plug in 2 for that, what do we get? So 2 minus 4 gives me negative 2 times negative 1 gives me 2 times 2 gives me 4. And so we know we have a parabola here. If I wanted to come up with parametric equations for this, it's easy enough to just have x of t equals t and y of t equals, I'm going to go ahead and distribute that. So minus t squared plus 4t. And those are easy parametric equations. And again, if you want, come up with a table. When t is 0, x is 0, y is 0, that's this point. What happens when t is 1? I get x is 1, and y is, let's see, 1, negative 1 plus 4, y is 3. So we'll be up here on the parabola. T is 2. Essentially just computed that guy. My x is 2, y should be 4. And likewise 3, 3. And then if we plug in that, so it'll be negative 9 plus 12 will be up at 3. Let's do one more example. So, of course, this isn't always the case with functions. Sometimes we're given these curves as equations, as implicit equations, and I'm not always working with a function to start with. So our parametric equations give us this opportunity to sort of broaden our scope of equations and curves we can essentially model in space, and give us some new tools for doing calculus. So we've seen implicit functions, and we've done implicit differentiation in Calc 1. We're essentially just going to come up with some different ways of doing that. So sometimes implicit equations are either hard to come up with, or they're just not nice to solve, not nice to differentiate, and it's maybe a bit easier to do parametric equations. So let's do another example. Let's give a parametric equation. Cosine of t is x, and y of t is sine t. So this one we can't solve for x as a function of y, or vice versa. Because if we did so, we would have to use our inverse functions. And the problem with our inverse functions is that they're only defined on a small segment. Whereas the natural domain for cosine and sine is all the way from 0 to 2 pi. But if you remember from your pre-calc, the arcsine and arccosine, we have to essentially restrict the range so that it maintains this notion of a function, so that it still has one output for a single input. So what's this going to look like? How do we graph something like this? Let's make our table. And let's pick some values. Maybe we'll start, let's put 0 in the middle. We'll leave some space for some negative values we might want to check. So when x is 0, my x-coordinate is 1, and my y-coordinate is 0. We have trig functions, so maybe we will use time values that are nice enough for those. Things like pi over 2. Let's do pi over 4, actually, first. And pi over 4, I will get square root 2 over 2 for both sine and cosine. We'll do pi over 2 next. Cosine is 0, and sine is 1. And then let's just keep doing multiples of pi over 4. So 3 pi over 4. My cosine is negative square root of 2 over 2. Sine is positive, still in the second quadrant. And let's do a couple negatives. So if I go negative pi over 4 when time, negative pi over 4 puts me in the, oh no, so I set my domain from 0 to 2 pi. Oop, I'm not following my own directions. So if our domain goes from 0 to 2 pi, we only want to consider time values. So starting at 0 was the appropriate thing. We've got up to 3 pi over 4. Let's see, we got more space on the camera. Let's go up to pi, and then if we want, we can make another table for the second half. So at pi, cosine of pi, sine of pi, 0. And let's plot this now. So at time 0, I'm at the position 1, 0. So let's make it pretty big on the axis. So sine and cosine, of course, are bounded by 1. So some things that this tells me. Well, if I'm just looking on the x-axis, we have cosine. And I know cosine is bounded between -1 and 1, which means on the x-axis, we're only going to move between -1 and 1. Likewise with the y-axis. Sine is bounded between -1 and 1. So on the y-axis, or at least in the direction of y, we are going to be bounded between -1 and 1. And if we plot our points, we've got 1, 0, we've got root 2, or 1 over root 2, 1 over root 2. That one's going to be a little hard to draw. It's going to be about right there. Then we've got 0, 1. I've got negative root 2 over 2 and positive root 2 over 2 in the y direction. And then -1, 0. What's this look like? Can you guys guess? This gives us a circle. Let me try to draw it here. And if we were to keep adding points, it would go around. So that's kind of nice. We know our trig functions, they oscillate between -1 and 1. And of course, the equation for a circle, x squared plus y squared equals r squared, not a bad equation. But now we have another way of modeling a circle. And we can actually expand on this and do some more advanced things as well. Some other ways we can kind of intuit this of how to get a graph from a set of parametric equations. We really want to think of it as a particle moving in time. So sometimes it's helpful to just plot where am I at time 0 and then moving forward. So time 0, we started here. Well, since x is cosine, let me try to squeeze these in here. If we were to just plot the x coordinate, cosine starts at a peak, comes down, and then comes up and ends at a peak. So this was 0, this is pi, and this is 2 pi. So at pi, we're at -1, and at 0, we're at +1. So if you look at my x-coordinate, how does this trace my x-coordinate in time? You can kind of think the motion of the particle, if you project everything onto the x-axis. Well, if I were to move around this circle, what's only the x-coordinate doing? It's starting at 1, but then it's decreasing. And then my x-coordinate hits 0 at pi over 2. Then the x-coordinate is going to be negative until, I'm tracing too fast on the bottom one. It's going to be negative until we hit pi, and then it'll reach its maximum negative value at -1. And then it's still negative, but now moving back forward, my x value is starting to become positive, and then hits 0 at 3 pi over 2, and then comes up to 1 again. Everyone kind of see that? And we can do the same thing with our y-coordinate. Since y is sine, what's sine going to look like? Something like this. It's going to start at 0. What's the y-coordinate here? So now we're thinking about sort of projecting onto my y-axis. If I'm here, my y-coordinate, 0. And then, but as time increases, we're moving around the circle. My y-coordinate's increasing. I'm going up on the y-axis. Then I hit my peak. We keep going. I come back down to 0. Then we keep going. We're negative y-axis. Hit our peak at -1. And then we come back up to 0. Does everyone see how that works? So let's do one more. Something like this again, with these sines and cosines, of just trying to plot it. Actually, we could do a couple. We could do some other easy ones. Let me see. Which one did I have written down? So one way of writing parametric equations So, well, we have xy coordinates. And if really all I'm doing is keeping track of the x coordinate and y coordinates, we usually give our coordinates as ordered pairs. So we will often list equations as an ordered pair, except we just change the brackets. Instead of using round brackets, we're going to use angle brackets. And we can actually call this, sometimes we call it the position vector. You'll learn more about vectors in Calc 3. This is sort of a baby introduction to them. A vector you can think of just as a mathematical object that has a length and a direction. And so what we kind of want to think of it as, well, if I'm starting at the origin, this is just pointing to wherever the position is of my particle. So in our previous examples, you kind of think, well, what's my position relative to the origin? It's here. Then as time moves, now my position's over here. Then my position's over here. Ooh, I guess you guys didn't see that. Sorry. So relative to the origin, my position's here at one time. Then as time moves, my position is here. And really, you were just keeping track of the XY ordered pairs. It's really how you want to think about it. This R is kind of just a shorthand notation because we have kind of introduced this extra time variable, and now we have time as an independent variable, and we have essentially two dependent variables. So for shorthand, a lot of times we just kind of write a combination. We write this R to mean the combination of our X variable, our Y variable, and our Z variable sometimes if we're in 3 dimensions. So for example, I can write parametric equations like cosine of t and let's say sine of 2t. This just means, so if I write something like this, it's the equivalent of saying that my x of t is cosine of t and my y of t is sine of t. Because of their positions, it's implied that that's x and that's y, listed as an ordered pair. So let's graph this guy. This one's going to be a little weird. And again, let's set our time values between 0 and 2 pi. I've got sines and cosines, so I'm going to oscillate on the x and y axis. And I know that there's no constants out front, so the maximum y value is 1, -1 for the minimum y value, and the same thing is going to hold on the x axis. So my maximum values are 1 on either axis. So how is this guy different from the circle? If I were to look just at the x-axis, well, I'm oscillating on the x-axis as a cosine curve. If I were to look at just the y-axis, I'm oscillating on the y-axis at the sine curve, but what's happening with the y-axis? That 2t is going to mean we're going at twice the speed, is essentially what it means. I'm taking all the t time values and I'm multiplying by 2. So I'm going twice as fast on the y-axis. Let's plot a couple points again. 0 is easy. So 0, I'll have cosine of 0 is 1. Sine of 0 is 0. So I'm starting at the same point. What about pi over 4, though? Okay, well, x we get root 2 over 2. When I multiply by pi over 4 by 2, I get pi over 2. And so I just get 1 here. Okay, so we will have root 2 over 2, which is, about here. And then I'm all the way up at 1. And I go from this point to that point. And then my pi over 2, well, x is 0. Cosine of pi over 2 is 0. When I multiply that by 2, though, I will get sine of pi, which is also 0. So we get to 0.00. And if we keep going with my 3 pi over 4, my x will be negative square root of 2 over 2. And my y, so 3 pi over 4 will give me 3 pi over 2 after I multiply it by 2, and sine of that gives me negative 1. So over here at root 2 over 2, we're down at negative 1. And what's happening at pi? Cosine of pi is negative 1. Sine of 2 pi goes back to 0. So we're going to be here. So what's happening with this guy? You can see like they're both oscillating, but the zeros of sine, like the zeros and the peaks of x, are the normal values, y is hitting its zeros and its peaks and valleys twice as fast. So the curve's going to start here. Remember, we started here. We go up. I hit this guy. Then we come down to the origin. Then we hit this guy. And then my last point we ended with was here. That was the first half of our interval. If we go all the way to 2 pi, let's keep doing this. So what are our next values? So after pi, we've got 5 pi over 4. And we've got negative square root of 2 over 2. We will have sine of 5 pi over 2, which should give me 1. We will have, so a point up here. And we can kind of see, so my x's hit their peak. My x's were at -1 at pi. My x's are going to start coming back this way. And my y's, in many ways, are going to repeat as well. And so if we check the next one, so 6 pi over 4, 3 pi over 2. My x is going to be 0, cosine of 3 pi over 2. And my y now, sine of 3 pi, when we plug that in, gives me 0 as well. So we go back and we hit the origin again. And then the last point, last 2 points, I should say, 7 pi over 4 and 2 pi, where you guys think they're at. So 7 pi over 4, cosine is positive in the fourth quadrant, so root 2 over 2. 7 pi over 2 gives me a -1 for sine. So when we multiply that by 2, we get 7 pi over 2. And then, of course, at 2 pi, I'll just get, cosine of 2 pi, 1, and then sine of 4 pi gives me 0. So we had our origin, and our last point is going to be about here, and then back to where we started. So the rest of the curve comes up, comes down, and then comes back up. Any questions on that? So this is just the basics of graphing. Let's write some of these tips down. So plotting tips. Make a table is one strategy. Other things you can look for is project onto the x or y axis. So look at those curves. Independently. And then combine them. It's kind of what we were doing with our previous example, our previous circle. When we consider our separate graphs. So we kind of consider the graph of cosine, and well, if this means my x value starts at 1, and we can kind of see what the x coordinate is doing. So we modeled what the x coordinate was doing, and then the y coordinate simultaneously starts at 0, then goes up and down. And if we do those at the same time, my x is going to start here, y coordinate goes up, x coordinate decreases, and we get our nice circle. Let's try to model of what's going on that with here, right? So our x is kind of doing the same thing. If we trace just the x coordinate of these points that we traced out, as time progresses, my x coordinate, you can imagine just projecting the curve down to the x-axis. And what's happening with the x coordinate? It starts here, decreases, hits 0, hits our -1, and then as the curve started to go back up, my x-coordinate started to increase again. So it just oscillated like a cosine. But what did my y-coordinate do? Did the same thing, just twice as fast. So my y started at 0, went up real fast, back down to the origin, went down real fast, back to the origin. So that's like this point. And then we went up, and then we went back down, and then decreased to that minimum, and then back up to that point. And then, of course, the last thing you could do is to try to write it as a function. Which we kind of saw in one example. Let's do one more of those. So let's say I give you parametric equation of minus 2t and t plus 4. So again, this is the equivalent of writing just x of t is minus 2t and y of t is t plus 4. So it's not quite with some of the easy functions we started with, like x of t is just t, and I could easily recover the function. This one, well, I have x of t is negative 2t, and y of t is t plus 4. But it's also not as complicated as like the sines and cosines. The individual functions, x of t and y of t, are linear functions. They're basic, first-order functions. So how can we recover a function for this? Well, we've been doing those skills all along with u subs, and probably have done this quite a bit in pre-calc with linear equations. If I have x is minus 2t and y is t plus 4, we can always take one of the equations and solve for t. If I want to get rid of t in my y equation and substitute in x's, I just take the first equation and solve for t. And then I plug that in to the second equation. And we recover our function. What's the graph of this guy? Well, we've already seen this graph, actually. Sorry, let me turn it myself so I can make sure I'm plotting this correctly. So we've actually already seen this. We started with our example of x of t is t and y of t is minus 1/2 t plus 4. This was our standard way if I was given this function to start with. and I wanted to write a parametric equation for it, the standard way of doing it is just to say, let's let x be t, and then replace that x in the y equation with a t. So what's different about these three equations? I'm already using letters. Let's call this A, B, and C. So our big note, our observation, so there are multiple ways to parametrize a given curve. I'm going to do a couple more examples after we kind of talk through this one and try to figure out, well, what's going on? Right here I have different equations for my x's and y than these two x and y equations. But they both resulted in the same graph ultimately. So is one more useful than the other? What type of information is carried? What else do we get from these parametric equations? There seems to be some added thing going on. Beyond, well, B is pretty easy. We've seen B and know and love and study this type of equation since pre-calc, right? It's just a straight line. And all the information that's carried in here is just the relationship between my position of x and my position of y. And we plot those on our points. That's essentially the only information that is carried in that type of equation. So our other notion is parametric equations contain more information than just points in position. Let's draw our table. So we have our t, we have our x, we have our y. Let's call this one for A. Let's call this one, then make another one for B. And just do a few points. Namely, let's pick t equals 0. What did we have in our first one? So we've made this table, 0, 2, 4. And then so for our B, for our C, when we started with, we had our x is 0, 2, 4, and my y was 4, 3, and then 2. So in some sense, what this is saying is when time is 0, we usually consider time 0 as our starting time, right? Let's see, maybe I can get a different color. Let's get green, see if that'll show up. So at time t equals 0, we start here. And then I am at time 2, I'm over here. Time 4, I'm over at this third point. So what does that tell us? It gives us a direction. It says I'm starting here, and as time moves, we like time, and time has essentially one direction. Of course, in our math land, we consider negative times. But even if I start at a negative time and move forward, it's always moving forward. So you actually hear this a lot in space flight. I don't know if you guys have paid attention to any of the recent SpaceX launches. Anytime you hear the phrase T minus 15 seconds or T minus 20 minutes, that minus is in an actual minus. It's a negative value. It's a negative time. Because time, as we measure in our physical universe, we only have time as one dimension. It only moves forward. And so what we're essentially doing is just putting our reference point, we're putting our 0 hour in the future, launch time. So our launch time is in the future. And what time is it relative to the launch time? It is negative 15 seconds. So really a countdown is actually a count up. We always count forward. We're just starting at a negative time, counting forward. And so because of this time moves forward, we get a notion of direction on the curve. So here we started at 0 and now we're moving in this direction. So this other part of the curve, even though it's negative, we're still moving in that direction. And so if we wanted to add another point, say t is equal to -2, what's my x going to be -2, and what's my y going to be up at 5. So even though I have other points on the curve that go back to -infinity, I'm moving along this curve in the lower right direction. What's happening with our curve A now? Well, at time t equals 0, let's see, can we get both of those on the screen? Maybe we can rewrite it. So here we had our x of t as -2t, and our y of t is t plus 4. So at 0, we're still getting the point 0, 4. We're starting at the same position. Here, let's do these in green. I'll have to move that up. Let's make the table here real quick. What happens when t is 1? Well, now my x value is -2, and my y value is 5. What happens when t is -1? My x value is 2, and my y value is 3. So let's plot those. Well, we actually already have those points. We have the point -2, 5, and we have the point 2, 3. But what time values did those correspond to? This was t equals 1. This was t equals -1. So what's going on with the green parametrization? I'm still starting here, but now I'm actually moving in this direction. So we're moving in the opposite direction of the curve. And not only that, well, what happened? How many seconds did it take me to go between this point and this point on my pink, on curve C? It went from -2 seconds to 0 seconds to travel between those 2 points. My green curve, I'm going in the opposite direction, and how many seconds did it take me to travel between those 2 points? Just took me 1 second. So not only are there position, I guess we didn't finish that note, are parametric curves and specifically, I guess I should say parametric equations. Beyond just the position of the particle and the shape of the curve, they contain information about the direction of travel and speed, how fast we're moving along the curve. And these are very calculus-y things that we're going to get into. Speed in particular. So how have we measured speed in the past? we're actually going to measure it the same way. Speed is just the derivative of position. Now we just got a little bit more to think about, because now I don't just have y as a function of x, and I can't just take a derivative that way. I have two dependent variables, x and y, and we need to take our derivatives. Well, how do I take a derivative of time? We're actually just going to be able to do that in each coordinate. And as I take, position as a derivative of time, it'll give me a notion of velocity or speed. Does that all make sense? So let's do one more example. We've got 1 minute. Let's just go back to our circle. Let's do a couple parametrizations. So what did we find with this guy? We started, x was 1, y was 0. And as time increases, sine starts to increase. So my x value is going to decrease, but my y value is going to start increasing. We're going around the circle counterclockwise. And so we can figure out our direction essentially by tracing the direction of time, exactly like we were doing with our tables. As time moves forward, what direction are we traveling in as we picked our points? With this guy over here, you should kind of see that, well, I've got the same functions, sine and cosine, in the same positions of x and y. It's just that my y is negative now. So instead of moving upward initially, what's going to happen? Well, I'm still going to start here. Then as time increases, this will be flipped. So it's going to be decreasing. So we'll still get a circle. We are just traveling in the opposite direction. Not the best of circle drawing there. So here we're going around this way. The third thing, let's write one more, and then we can end it. So 2t sine of 2t. We've seen what happens when I change the period. If the periods don't match up, we get these fancy infinity signs. But here the periods are the same. So sine and cosine, my x and y values, the periods are going to be the same. What do you think is going to happen in this case? I still get a circle. And again, not the best circle drawer. And, well, the signs match up this guy, so we're still moving around in the same direction. But how do the two t's affect it? What's going to happen? How many times, if my period were 0 to 2 pi in all of these? Here we saw 0 to 2 pi is just one time around the circle. How long does it take me to get around a circle if I'm doubling my t's? Just pi, right? I'll go around, and then pi over 2, I'll be here. When time is pi, I'll be back all the way around. So in this case, in this time interval, we actually go around twice. And so not only do we have these notions of direction, but now we got to figure out, how do I recover this notion of velocity from these curves? Some of it you can kind of intuit from, any scalar multiple of time, but we want a much more mathematical way of determining velocity. And we'll do that with our calculus. So that's it for today. Let me know if you guys have any questions. Otherwise, I will see you guys tomorrow.
I had a question regarding a textbook question.
Yeah.
So I'm going to pull up the solution right here so I can kind of see what they did. So I'm working through these parametric equations. And it's making sense for the most part. However, there's this one in the textbook. So we're given we're given that x is equal to t squared minus 3, and y is equal to t plus 2. And we're given the bounds of -3 to 3. So the question asks for us to just, first of all, sketch this curve by just plotting points, which I did easily enough. And then the second part is eliminate the parameter and like convert this into a Cartesian equation.
Yeah.
Which, let me see, I think I took a picture of what I got.
Is this what you had? Sorry, let me make sure I wrote it correctly.
Y is t plus 2 and x is t squared minus 3.
Minus 3.
Yeah, so the way I did this is I just took x equals t squared minus 3. I solved for t squared and got t equals square root of x plus 3. Or I guess solve for t, not solve for t squared.
Okay.
And then I plugged that in and I got y equals square root of x plus 3 and then plus 2.
Mm-hmm.
And that's where I stopped. But when I'm looking at the solution, what they did here was they pretty much ended up changing their bounds and rewrote their equation as x equals y squared minus 4y plus 1, and their bounds was -1 to 5.
Yep. So you want to be careful with that. So just with our notion of functions, right? If I want to write, here I have x as a function of t. But if I solved for t, anytime you apply a square root yourself, you have to include a plus or minus. And so the problem is t is not actually able to be written as a function of x. You have to break it down into two functions, a positive function and a negative function.
Why do you have to include the plus and minus? Is it because t could be
T can
negative?
be
So
negative. Yeah.
squared? Okay.
Yeah. Right. I can
Okay.
plug in negative values for t here, but if I only kept the positive, I would never get a negative t value.
Okay.
And so it's not wrong. And then if you tried to plug that in, of course, you would get the y as two functions of x.
Right. You get, would that be like a piecewise type thing?
Yeah. And so conversely, kind of like I was saying at the beginning, well, we have functions of y and functions of x. And we kind of want to get out of the notion that y always has to be a function of x and start to think more of, well, it's just good enough to still have x as a function of y. And so your choice of independent variable versus dependent variable comes into play here. Since we want to write it as one function, it's best to pick x as our dependent and y as our independent.
So solve, instead of solving x equals t squared minus 3, solve y equals
Exactly. And I would say in general, I would do that. You know, if you're trying to recover an actual function, and it doesn't matter y as a function of x or x as a function of y, start with this one's way easier, right? Y is t plus 2. It's much easier to solve for t for that one and then plug it into the other one.
So if you do that, like, so what was going on with the solution where they're messing with the bounds? Because I haven't had to do that on any of these so far.
What were the time values?
So it's -3 to 3. And then they ended up they made like an inequality where they had -3, and then they swapped out t with y minus 2.
Yeah.
And then solved that inequality and got -1 to 5.
Yep. So those will give you your y bounds. And so and again, it kind of depends on what we're going to use as the independent or dependent. It would be different here. I would have to solve for the bounds of x corresponding to those values of t.
So if you're given bounds and then whenever you put this thing in Cartesian form, do you have to solve for the bounds every time? Because you have to are you like not re-indexing, but redefining, I guess?
Yeah, so because parametric equations, it's kind of like setting a domain of a function.
Hmm.
We've we're defining the domain. Since we're defining our independent variable as time, this is our domain for time. And if I want to recover a Cartesian equation for it, well, then I need to find the corresponding domain. And the examples, it's a little hard to see that we were doing that in class, but like right with our circle, my domain was only 0 to 2 pi, so which means I start and end at the same point. If I were doing like a parabola, so here because I specify time as minus infinity to infinity, well, that's the whole parabola. But if I only picked time from like 0 to 4, it would only be this top arch and nothing below that. So I would want to make sure that if I'm only including this top arch in terms of my time parametric equations, I want to include only that top arch for any other Cartesian equations that I come up with. So we just have to set the domain appropriately. And
Okay.
you determine the domain by whatever equation you're solving for. Like we solve one of the variables for t, use whatever that equation is in that uh, in the domain equation.
Okay, that makes sense now. It's not a difficult concept, just understanding what was going on.
Yeah.
The other one I had a question on, mainly just the bounds. Um, so we're just given like t plus sine of t, and then y equals cosine of t, or x, sorry, is t plus sine of t. So your bounds is negative pi to pi. So when I was graphing this, I kind of found myself like, okay, so I'm thinking if I go negative on the unit circle, you go, instead of going like up and to the left, like first to second quadrant, don't you go fourth to third? Isn't that how that works? So like you would go,
Yeah.
because so to get from like negative pi to zero, you'd have to go negative pi, negative 3 pi over 2, and then you get back to zero, right? Or how does that work?
Yeah. So are you talking about just how we're traveling around t?
Yeah, I'm just trying to think of like if I'm gonna plot this thing, um, the values of t that I need to be using.
Yeah, I mean, so t starts at minus pi, goes to pi. You can kind of think of it as starting at the left end and then going around all the way back to that left end
Okay,
circle.
just making sure because like whenever you go around the unit circle, you go counterclockwise. So then whenever you go in the negative direction, that's clockwise, right?
Well, so you don't want to quite think about it that way, primarily because time. We want to think of time, even though the values are pi. It's really just a straight line. What was the y equation?
I think it was just cosine of t. Yeah, just cosine of t.
And so what you kind of want to think about now is, well, we have this time, which is on a straight line, one dimensional. And what we're doing with this parametric equation is then mapping it into the Cartesian plane, primarily moving in this direction. So it's like I'm starting here and ending here. The values on my line are pi, and then we're mapping this line into the Cartesian. But it could be, if I'm taking this line segment, I just have to trace out how we're mapping this line in
Right.
the Cartesian plane.
Yeah, I think the issue is just not knowing what's between negative pi and zero, which my intuition is negative 3 pi over 2 um, instead of like pi over 2, but I'm not certain because I know, 0 to pi, that's easy, but whenever it gets negative, it just gets a little.
Oh, I mean, well, so pick a value here. What's your favorite value in between here?
I don't know, pi over 2.
Pi over 2. So negative pi over 2.
That's it. Okay, I guess I'm thinking about moving around the unit circle instead of how you said, like on a straight line.
Yeah, I see what you're saying. Yeah, and it's easy to get confused, especially with as much as we hammer trig at you guys in pre-calc to kind of think of it that way. Uh, yeah, because I mean, it's not wrong. The thing is, like 3 pi over 2 is here. The problem is if we're counting this as negative pi, means I'm back around this way, which means when I'm here, I'm at negative pi over 2 to 0 to pi over 2 to pi.
Okay, that makes sense. That makes more sense. Yeah. Okay. The only other question I have, so understanding like what a plane curve is. Okay, so I understand kind of the problems with them, which is like sometimes we're not really given a direction. Um, the curve may not be a function, or it might not be like explicitly a function of uh, x or y.
Mm-hmm.
But what is like? I'm trying to think of what is a plane curve. I think it like I don't know. I'm thinking of it in like a three-dimensional space because that's what makes more sense to me when I think of like a plane.
No, if it says a plane, 2-dimensional space.
Is it two-dimensional? Okay.
Yeah, a plane curve is just a curve in the xy plane, in the Cartesian plane. So anything that you can just put your pencil down and draw, it doesn't even have to be smooth. It could be jagged. Is a
So
curve.
is it basically a curve? Well, like in this case, we're using parametric equations to solve or graph um, curves that are not functions, pretty much.
Yeah, or curves that are functions. Either one. Yeah.
Okay. I'm just trying to understand the theory behind what's going on here.
Yeah, it just gives us a broader tool. So it's kind of what I was trying to hint at is that like we can graph all of our standard functions with parametric equations. But now we can graph an even broader classes of functions. We can graph anything, even functions that like loop around themselves, and or I guess not I shouldn't call them functions, but curves that loop around themselves and can do any kind of fancy things. It just gives us more tools to work with in terms of our mathematical modeling of motion, really.
Okay. Um, as for the final, you said you were gonna give us like or hint to us what topics are gonna be covered more frequently on the final.
Yeah.
Okay, good, because that'll be useful. We have a lot of stuff to go over.
Yeah, I mean the final will be cumulative. It'll probably be weighted a little bit heavier with in terms of the material, in terms of the most recent stuff. Um, but I could tell you, what are the main topics if there's like a large chunk of a lot of Taylor
Yeah.
series or something like that. I'll make sure to let you guys know.
Okay. Yeah, it's just like little things. Like I feel great about like integration by parts, partial fractions, U sub, trig sub. I think I need to review for sure. Um, disk and washer. I probably